So today I'm going to try to give you a little bit of background with the amount of time I have about what geophysical imaging is and some of the constraints, and the uncertainties more than the constraints. But I'm not really going to have a lot of time to go into the details. So I just encourage questions or coming to me after the talk if you want to understand more how we interpret and judge each other's work when it comes to believing what's been published in terms of an image and how reliable it is. Okay, so the motivation is pretty obvious for the people in this room, right? Fluids are a critical aspect of Earth processes, tectonic processes. And the focus has been a lot on volatiles at arcs and subduction zones, and I'm going to kind of stick with that theme. So, of course, like Tobias said, rifts and mid-ocean ridges are a big part of this system as well. But for today, I'm just going to focus on subduction zones where we have inputs with the slab and then release of those fluids that drive arc faulting stuff. But those fluids actually affect a lot of other processes as well, such as the seismogenic zone, which we haven't discussed all that much during this meeting. So what is geophysical imaging really useful for? Well, it gives us a snapshot of what the fluxes might be like inside the Earth. So not just where they're going in and where they're coming out, but the processes in between those two stages. And so we can try to answer questions of how much water is actually subducted that we're not necessarily directly sampling, right? With the crust, with the mantle of a subducting slab. Where is it being released? How is it distributed? And where is it going? And then on top of that, how it's affecting a lot of different processes that we care about. And so I'll try to show you, I'm biased. I'm a electromagnetic geophysicist, so you're going to see way more EM images than seismic images, but there is a very rich literature, much more so, from seismology than there is from EM. But I think EM is going to be really exciting to show here because we are primarily sensitive to fluids, whereas seismics gives you a lot of additional information, not necessarily specifically sensitive to fluid processes. So this is my very optimistic outline. I have a lot of information. Hopefully it doesn't blow over you. And I'm not sure I'll get to the very end, which is what I'm actually most excited to show all of you about, but we'll give it a shot. So first, I'm just going to give you a couple slides on what geophysical imaging is and what it can tell us. Then I'm going to go to, pick up the point here, quantifying some input fluxes. So Terry gave us a really nice overview a couple days ago about the hydration state of a subducting plate. And I'm going to give you a little bit more detail about where things stand. So there's been really a lot of new knowledge gained through the Margins and GeoPRISMS program. By the way, I am absolutely a GeoPRISMS baby. So my first meeting was in New Zealand in 2013, and that was like the most inspirational experience. This is why I'm here today, seriously. So it drove the New Zealand project. So I'm looking forward to supporting what it does for all of you. Yeah. So and then most of the slides are going to be on inputs. There's way more information out there on outputs, actually, because people love to image the entire subduction system, right? What the slab's doing, all the seismicity, fluid that eventually lead to the arcs. I'm only going to show you one example, and it's new and unpublished, but the reason I'm going to stick to that one is because I want it to essentially get you excited about what's to come, as we're really a much more integrative community than I think in past generations of people sticking inside their own areas of expertise and only talking to each other. I feel like our generation is much better about getting together and trying to tackle these problems from different perspectives. And that's what excites me the most. Okay, so, and then I'll end with the thing I said I'm most excited to show you. Go do that again, which is a really simple strategy to combine geophysics with petrology and thermodynamics.
You have to do that.
I'll do my best, I promise. And it's so simple, and you don't even need new data to do it. You can go find your favorite geophysicists and team up with them and reanalyze existing observations, especially at arcs. So here goes. I hope I get that. All right. So the geophysics for dummies intro. I feel like geophysical imaging, that kind of expertise, is more like you do a lot of things relatively well, but you're not actually an expert in any one thing. You have to kind of combine a lot of different expertise to get to what you ultimately want, which is an interpretation of some image of the subsurface of the Earth. And so that involves going out to collect data, and that is in itself a specialization in an art form, right? How do you collect good data? Where should you collect it? How should you design these surveys? So that goes into the measurements part of it. We take those measurements home, we process them into a different type of data that we ultimately want to run into geophysical inversion. those processing steps also have a lot of intricacies and decisions that are made. And hopefully you get some understanding of the uncertainties in your data before you feed them into a geophysical inversion. The biggest step, I think, is the inverse method, right? So this is truly an art form built on math and physics. There's just so much wiggle room in an inverse image that you see. There's a lot of decisions that go into how to parameterize it, how to smooth things, where do you put sharp boundaries, a lot of decisions that people work really hard running hundreds and hundreds of these models before they settle on the one that they publish. So they have a lot of knowledge about what works and what doesn't. It's just really hard to translate into a paper because you'll just bore everybody, essentially. So most of these images you've been seeing are what are called deterministic inversions. I'm not going to be able to get into the details, but a deterministic inversion is one result. In inverse theory, we're working with mostly nonlinear data, nonlinear inverse methods, and uncertain data, right? All data have noise. By theory, there are an infinite number of models that fit your data. That's a lot to absorb, literally an infinite, but you only get to see one. So now we're making progress on stochastic methods that you won't get to see at all here, but it bodes really well for the future where we're actually understanding within a single image what those uncertainties are so that we can translate that to uncertainties in terms of the material properties we're interpreting from them. And so that's this last step here, right? I think the funnest step. It's a combination with laboratory studies, which all have their own uncertainties as well, to get at material properties you care about. And then you take all that and do the fun stuff, the interpretation of what it means for Earth processes. So there's a lot involved in this. And that's about all you're going to get from it on this topic. So we'll just go into what it can be used for. I wasn't able to produce a comparable figure for seismic velocity. So I apologize for that. But I encourage seismologists in the room to tell me where that exists, or if not, to make one, because I think they're very useful for non-seismic or geophysical imaging people. So this is what electrical resistivity can tell you. So you may have seen seismic velocity and what it can tell you. So hopefully that grounds you. So seismic velocity usually ranges between, let's say, 1 and 8 kilometers per second, right? Within an order of magnitude. Electrical resistivity in ohm meters, or its inverse, 1 over it. Conductivity, I'll often switch between the two. Something that's resistive is low conductivity. Something that's conductive is low resistivity. It scales in these types of images over 5 orders of magnitude. In reality, in pure materials, it's 20 plus orders of magnitude. It's really, really large. So we have a much different type of dynamic range we're working with. When you see a few percent velocity change, that could be a really big deal, right? A few percent resistivity change means nothing, almost nothing. It's usually you're working in orders of magnitude. So in this representation of what resistivity can tell us, it's really all about mixtures of things that have fluids in them. The fluids are often electrically conductive, either because, let's say in aqueous solutions, water, right? If a lot of salts are soluble in it, those become ions. They're like electrons zipping around. They make things more conductive. So that's what you're seeing up here. Even fresh water, this is in practical salinity units. I think 0.5 is the max for drinkable water. WHO standards are 0.2 or less. It's actually relatively conductive. Pure water is extremely resistant, right? Because it has no ions. The pH is what makes it conductive. But it's like 10 to the 5th, 10 to the 6th ohm meters. Seawater is incredibly conductive, and notice that there's a lot of information on here. It depends both on the salinity content and the temperature of that fluid. Pressure also comes into play when we're talking about things in subduction zones. But anyway, these things are, these colors you'll see in the inversion models I'll show, they're in the yellows to reds. Most of the stuff we'll be dealing with in subduction zones, the fluids are red, so are the magnets, right? So here's a pure mafic melt. In the melt, we're sensitive to its composition as well. I'll get to that in a second. So otherwise, you have relatively resistive stuff, and what's driving it to be more conductive is how much water is in it, what its porosity is. Okay, and so we can use mixing relationships to make estimates of how much water is there. One of those types of mixing relationships is Archie's law. It's a classic empirical relationship that's, I think, from 1942, something like that. There's a lot of versions of this. There's also theoretical mixing relationships. Either way, they take a bulk measurement. This is bulk resistivity, something I would observe in my data, and then relate it to some material properties in terms of a mixture. In this case, a fluid mixed with a solid. The solid is infinitely resistive, so you don't actually see it in this equation. There's the cementation exponent. That's kind of like the topology of the pore network, the interconnectivity. And we have constraints on that from laboratory experiments with different materials. Usually, we just kind of use a number and slide that under the rug. But it is a source of uncertainty, but it's okay. It's not the biggest one. And you can use a range, right? Say if I don't know it exactly, here's a range. This is how it affects my absolute values, but the relative changes I see are pretty well constrained. Then you have your porosity. So let's say I'm interested in the porosity. It's some function of the fluid resistivity with the porosity to the cementation exponent. So this is really important here because it depends on what your agenda is. Do you want to know porosity and maybe you know what the fluid composition is? You can do this. Or do you know the porosity and you actually want to know the fluid composition? Let's say for groundwater. How far offshore does fresh water extend, right? You make some assumption about its porosity, you can get at what its salinity is. This is also true for magmas, which I think is what all of you are interested in, right? The magma resistivity depends as a function of temperature and its volatile content, not just water, also CO2. CO2 has to be much higher, over 6 to 8% before it starts affecting things. And I'm sure other volatile elements that I'm less familiar with. The point being that I can not only constrain how much melt is there, I can potentially tell you what the composition of that melt is. And I think that matters for the folks in this room. All right, so inputs. Essentially take away message. There's really been a tremendous amount of progress in GeoPRISMS, kicked off by margins. But there's still a lot of huge questions left to answer. So one thing we kind of know now that maybe you can argue we already knew, the inputs are very heterogeneous. It matters where you are and what the local processes are, what's happening locally that affects the absolute input. In this case, the focus is on water. But again, the uncertainties remain large. So this is the pre-margin state of mind, okay? Everything happens at a mid-ocean ridge. You have altered oceanic crust because you have the hot water circulating right through the extrusive crust. That adds hydrous minerals. Eventually, the plate gets old enough, it cools down, it stops doing that. So you have some amount of hydrous minerals, some amount of pore water in your extrusive crust, and plus whatever sediments have settled that are then subducted. Okay, so folks thought this was pretty well constrained, right? We know what the inputs are. They vary regionally because of sediments. The oceanic crust is on average 6 kilometers everywhere. And as long as it's not super, super young, it went through the same amount of hydration, full stop, that's what's subducted. Obviously, we know that's not the case today. So what happens during margins, or maybe right before margins, right when it kicked off? This is really, I think, one of the first papers to suggest this idea. It's a really cool paper. I encourage you to read it. It actually didn't have anything to do with what's going on at the incoming plate in terms of what they were looking at in the data. They were looking at these two planes of earthquakes that happen in some subduction zones where there's seismicity at the plate interface and seismicity at some depth in the mantle that seems to scale with plate age. So Simon connected it to temperature. The temperatures, pressure ranges looked like where serpentinites might be hydrated and suggested, hey, what if fluids are moving through bending faults at trench outer ice systems and hydrating the mantle? And that's why we're seeing these 2 planes. Not long after that, a couple years after that, an image, a very famous image here from Renero et al. That Terry also showed, they basically saw these reflectors. They're faults, right? You're like, why is it a big deal that they image the faults? We know the faults are there. We know they're cutting into the mantle because of the deformation and the fault throw. Why does that matter? Well, you shouldn't see a fault because it's in the crust, because crust offset from crust, there's no difference in the material property. So why are they seeing faults? Well, they're suggesting it's because fluids are there that create a contrast in seismic properties that then allow you to see it. And they're seeing these penetrate past the crust mantle boundary, the WOHO, penetrate into the mantle. There must, if you introduce water into the mantle, it will serpentinize, right? Very exothermic reaction. It's going to happen. So this was kind of a big deal. And then since then, we've confirmed that, at least with what I did for my PhD. This was, by the way, I think one of the last margins funded projects. So I actually started off with a margins project, which is pretty cool. We used a relatively new technology that was developed for oil and gas at Strips, basically to use controlled source EM methods. I won't get into how it works, but I'm happy to talk to you about it after. But we can make a high resolution image of, let's say, the top 5 to 10 kilometers below the seafloor. Remember, the colors are similar to what I showed you before. Reds are conductive, it means they have fluids in it. You get into the blues, it's resistive, there's no fluids around. So you're seeing 400 meters of sediments in the red, extrusive oceanic crust. Then very quickly, you're getting super resistive once you're into the intrusive crust in the mantle. But then once you get these bending faults form, we are seeing those fluids penetrate into the crust. So we've confirmed, okay, this is very likely, yes, bending faults act as fluid pathways into the crust and mantle. There's all kinds of cool stuff here on the subducting side that I won't get to today, but this is a non-accreting margin. We can actually track these sediments subduct. They're not accreting, and we can estimate how the compaction is removing water from them. And then you can see some of them are escaping back into the upper plate and being released at seafloor seeps. So we can make estimates using things like Archie's law of how much porosity is there. The good news is out here before there's faulting, we're agreeing with those global compilation studies of what the porosity and the extrusive effects and gap roads are. But once we get close to the trench, we've effectively doubled the porosity of the intrusive crust. Porosity doesn't mean minerals making it down to the arc. We're not necessarily sensitive to the hydrous minerals. They're not guaranteed to be conductive. Some are, some aren't. So we need another way to take this information and combine it with something else to say, what does that mean about how much water is then transformed into altered hydrous minerals, which will matter more for the deeper processes. But the point being that the crust is subducting way more water than we thought itself, in addition to what I'll show you about the mantle. This for sure will add hydrous minerals as well. So it's an open question how much. And obviously it's heterogeneous. That's kind of not a surprise either. This was the next project of that type. This was offshore New Zealand. This was my first project as a PI, directly inspired by 2013. It took 7-8 years to get here, but it was pretty cool. It was a lot of fun. And Christine Chesley, who's the next big shot, I would say, in EM, which is really awesome, worked on this for her PhD. And essentially, this is a profile offshore North Island where there's slow slip events. I didn't even show you a map. I apologize for that. But that's not the point here, really. It's not about this specific subduction zone. I just want to show you that we covered a seamount, the Taronga Knoll, just because we were curious, what does the structure look like? And I'm really, really glad we did. Because, again, a lot of really cool stuff on the subducting side with fluids and earthquakes. I'm going to ignore that. I'm going to just focus on this side. Okay. So what we're seeing is the seamounts have incredibly complex structure. Must be full of fluids. Who knows what else is driving some of these conductivity? It could be some minerals. Wow, I am going really slow. So what we also see is that there's a fault on the flank here that, again, it's not a bending fault, but we are imaging fluids move down. And what's cool about this image is we have heat flow data that is decreasing. And so that's confirming that fluids are moving down. And with this, we can say they're moving down along this fault and hydrating the plate before it enters. Okay. This is a large igneous province area, so the crust is really thick. This isn't going into the mantle, but nonetheless, it's probably hydrating the crust at the very least. So now let's move to the serpentinites. I'm going to show more seismic stuff. Serpentinites are slow. Therefore, you can use seismic velocity imaging to say, is there a reduction in the mantle in its velocity? If there is, maybe we can assume it's because of this. How much is there? Okay. And there's been tons of studies from several subduction zones by now that confirm this, that see these reductions in velocity. The most recent of which I think is a really spectacular study using an epic data set, honestly. I encourage you to read it, where there's hydration in the mantle happening, not because of bending faults, but because the slab has to subduct beneath the pluton, forcing the plate to bend, which deforms it and lowers its velocity, meaning it's driving fluids down and serpentinizing this stuff, which is really, really cool. This is deep serpentinization, all because of subduction dynamics. I still have questions. Why is it going less serpentine as you go down? Shouldn't it stay? And I think there is serpentinization, but maybe not 80% here. But there's a reason for that. It's not just serpentines that lower the velocity. There's other things that happen. For example, cracks. Cracks also lower the velocity. This is a complex figure, but these curves showing these decreases in BPVS are for different crack geometries versus the black line is the alteration extent for serpentinization. Okay. So the point of this is, hey, you could have just cracks. It doesn't have to be serpentinization. You could just be cracking the stuff, adding fluid, and maybe a little bit of serpentinization. How do we really know? On top of that, is it wholesale serpentinization of the entire block? Is it serpentinization along really narrow fault zones? We're smearing, right? These images are smeared. We don't really know the geometry, and this will matter, especially in terms of how it subducts. One answer is that no, there isn't a lot of hydration. So actually, there's still debate about how much is there. We know water is entering, we know there's some, but how much is still up for debate, and we still need to make progress on this, okay? So I'm not going to spend time on this, so I can at least show you a few more things before my time is up. But the point is, it's not just faults, seamounts, subduction dynamics. There's a lot of really cool stuff happening that's adding fluids to the plate just before subduction, where things are colder, not like at a mid-ocean ridge. So the reaction kinetics will be different. The type of hydrous minerals you form will be different, and they'll have different stabilities of when they get dehydrated once they're subducted. So essentially, we need a lot more of the same stuff we've been doing, but we also need to integrate it more with advanced state-of-the-art stuff that's happening these days in terms of reaction-driven numerical modeling. Then we really need more laboratory experiments to help us interpret what we're observing. And I would say water is really awesome, but a lot of you care about carbon. We need to get the geophysicists, including myself, thinking about making estimates about these other volatiles. How does carbon affect conductivity and seismic velocity that we might also be able to make estimates on those volatiles and their fluxes as well. All right, outputs. I really do have only one example. This one you saw, I forget, I think it's Ipuko who showed this. Really cool figure. Cascadia from magnetotellurics, another electromagnetic method. So this electrical resistivity of fluids dehydrating, making their way up at some point, right, driving magnetism that then feeds Mount Rainier. So this is really cool stuff, and we need to see more of it, and we will. There's a lot more people who are interested in that. But I wanted to just show you one new result from Alaska. The image, another GeoPRISMS project. All of these projects tried to be co-located with existing active source seismic lines or planned together so that they're done simultaneously. This is co-located with the ALU projects, line 5. So I'm just going to show you the recent M2 result from this, and really only on the shelf. But I think it's a pretty spectacular image. When you look at it alone, it's seriously, it's like, what is this? This is the first time we saw this. We're like, oh, we're overfitting this data. We did something wrong, but for giggles, we're like, let's just start overlaying some stuff and see, is there any correlation with other observations in this area? Just the ground truth. Maybe we are doing things okay. This was a very recent paper from Donna Shillington using the active source seismic data for seismic topography. These are velocity lines. You can see a lot of agreement where there's blues and high velocities. And here's the plate interface, and maybe this is the continental mode. Okay, this is where it gets really cool, though, is this image. Okay, they image somewhere with the seismic reflectivity, something really weird is happening at the plate interface here. And they're not really sure why. They suggest maybe it's fault branching or fluid-rich layers. It happens here, and there's a bunch of seismicity offended. I think we've answered that question. There's fluids dehydrating, and they're moving straight up and interacting with the plate interface. And then they're diverting and moving more laterally because there's a giant fault cutting through here. So they're following the fault. Now, what's amazing about this is this is deep in the mantle. Why are there fluids coming out here? Well, the thermal models are suggesting this is consistent with serpentine dehydration. Again, why it's happening only here, who knows? Still a lot of things to answer. This is also preliminary, so things might change a little. These earthquakes might not really be there. This is a global CNT catalog, so this might not be really where those earthquakes are, but at least it's consistent with what we think we know. So it's not only affecting the arc, but it's actually affecting the seismogenic zone as well. So I think this is kind of the future of where we're going, is making more images like this, and we're really going to learn a lot. So this is kind of my hyperbole summary for this part. I really do, I'm very optimistic, and I really do believe we're on the verge of some pretty profound discoveries, because there's more people doing this and combining these kind of data sets. And I really think we'll see a lot of stuff that's going to surprise us and probably confirm a lot of what we're suspecting anyway. All right, do I have time?
Yeah.
I do. I appreciate it. It's not going to be that much time.
Yeah.
So this is one of my favorite albums from high school. It's called The Shape of Punk to Come, which is based on an album called The Shape of Jazz to Come. It's really loud and awesome at the same time because it merges different musical stuff together. And I feel like this is kind of the theme of what I'm going to try to show you here today, which is we can merge already with what we have geophysics and thermodynamics. How do we do that? So traditionally in geophysics world, we get an image. I don't have any images for you here, but you get an image somewhere at blob, whether it's low velocity or low resistivity. And it's in an area where we know there's magma, and so we want to make an estimate of how much magma is there. What do we usually do? We usually don't like high melt fractions. So to help us get to lower melt fractions, we increase the temperature, because increasing the temperature reduces the velocity or resistivity of the background. So you need less of the high conductivity or really slow stuff to mix into it to get to your observation. However, this is clearly not physically real, right? Because thermodynamics tells you if you increase temperature, you should have more melt stable. This is awesome, the fact that these cross. You can take advantage of this to force yourself into an answer that's both physically realistic if your thermodynamics are okay, and helps us not have that wiggle room to just say whatever number pleases us, because that's the paradigm, right? That's what the thinking is. I hope all of you will do this. You can do this with the resistivity and shear wave velocity. They're the same behaviors. Okay, so you can actually combine the two. We've already done this for an image of a lithosphere-asthenosphere boundary. Dan Blatter published a couple of weeks ago that you can go read. It's a really short paper, and it gets the point across. But you can also add what I mentioned really early on, which is stochastic inversion, which gives us uncertainties about our model. How well do we really know the resistivity of this blob we saw? Well, we can give some uncertainties on those and combine that as well. Eventually, with the help of you all, we can put uncertainties on the thermodynamics as well. And that's going to be really nice because it'll give you some realistic confidence of what you're interpreting. Okay. Now, in EM world, which seismics, I think, doesn't have this ability, we're also, like I said earlier on, we're sensitive to the volatile content of that melt. And we can include that in these calculations as well. So like I said, we did this for mantle melting, which is undersaturated, but you can do it for ARCS2. My postdoc has independently came up with this idea, by the way, which is pretty cool. At the same time, I was hiring him. I realized he was doing this already. He was working with Juliana Schrock at Smithsonian and with Chris Hubert. And I was so excited that he was already thinking about this. They made some parameterizations from rhyolite melts for a specific composition that I don't remember. And there's a bunch of lines on here. These are, some of these, the black solid ones are resistivity lines. Then there's the other ones that I'm honestly forgetting. The colors are the melt fraction. Here's where you get to saturated world, okay, down here. So there are examples I don't have time to show, but I haven't even included, where we're seeing stuff that we have to interpret as 100% melt that can't be realistic. Turns out it's probably because it's saturated and there's a third phase, right? We avoid saturated interpretations. We don't want to deal with it because it's hard. We don't know what is the third phase of the material property. The point being, if you have an estimate, you can combine it with these independent constraints on the thermodynamics and say, okay, here's my resistivity, this solid line, let's say these are our uncertainties. So if we're somewhere between 750 and 900 degrees C, I can tell you both how much melt there is and how much water there is, which is pretty awesome, okay? So I really do believe this is the way of the future. And I just wanted to end there and say thank you and thank you for the extra time.